Okay, so our goal here is just to do one problem. It's just going to be a weak base being titrated by a strong acid. In a previous video, we went over how to titrate a weak acid with a strong base. You'll notice they're very similar. The steps we kind of derive from those processes will be in this PowerPoint as well. So the actual problem that we're going to get into is this one. So we have 200 milliliters of a zero point 0.2 molar ammonia, which is a weak base solution, and it's going to be titrated with 0.5 molar hydrochloric acid, which we obviously know is a strong acid. Okay, so what will the pH be at the following amounts of HCl added? And you're given that the Kb is 1.8 times 10 to the negative fifth. Okay, so the first step that I do here, you might remember we kind of split these into three different categories, right? And so we split them into before the equivalence point, at the equivalence point, and past the equivalence point. Okay, and we're going to relate this to our weak species, right? So we're going to relate these numbers to the number of moles, right? Which we always use moles when doing titration problems. So we're going to relate to the number of moles of ammonia we have. So 200 milliliters or 0.2 liters of 0.2 molar ammonia tells us that we have 0.04 moles of ammonia. Okay, now how do we know which category each step of this titration problem falls into? So whenever we are before the equivalence point, we're going to have less moles of our strong species. So in this case, we're going to have less moles of acid than we do that weak base. Okay, and so for part one, we had 40 milliliters or 0.04 liters multiplied by 0.5 molar, telling us we have 0.02 moles of H plus. In part two, we had 60 milliliters, which comes out to 0.03 moles of H plus. Now, in both of these cases, we have less moles of our acid than we do our weak base, which is 0.04 moles of ammonia. And so because it's less, we know that we are before the equivalence point. Okay? The third part, where we have 80 milliliters or 0.08 liters of the hydrochloric acid solution, yields 0.04 moles of acid or H plus. Now, because that's 0.04 moles and our amount of ammonia is 0.04 moles and they're equal, that's how we know we are at the equivalence point. Okay, so that third part is going to apply to when we are at the equivalence point. And in the last part, when we have 100 milliliters or 0.1 liters of HCl solution, that tells us we have 0.05 moles of H plus, which is actually more than the amount of weak base that we have. And so because we have more of this strong acid species, we have actually passed our equivalent point. Okay? And so first we're going to look at what happens or how do we solve when we are before the equivalent point or equivalence point. Okay? And so these are just the generic steps. They're very similar to the one in the previous video. You'll just notice kind of the red portion. So our first step would be to write an ICE table for this, right? So we want to write our equilibrium in terms of our weak base. Then we're going to put our change in our ICE table in terms of the amount of hydroxide or H plus added. Okay, so on all these slides, I'm going to have like two things in red. The first one, so in this case hydroxide, would correspond if we started with a weak acid, okay? And the second one in all these parentheses corresponds to what happens if we start with a weak base, okay? And those are also bolded and highlighted or underlined. And so in this case, our change is going to be in terms of the amount of H plus added, with all that H plus coming from HCl, okay? Then we're going to find our equilibrium amounts in terms of acid and the conjugate, right? So of our ammonia, which is kind of like our conjugate or our base, and our acid would be ammonium, NH4+. After we find those equilibrium amounts, we'll find our pKa, and then we will plug into the Henderson-Hassel box to find our pH. Okay, so this is the math for when 40 milliliters of HCl solution is added, right? And you can go back. We found that when 40 milliliters of 0.5 molar solution is added, that means that we are adding 0.02 moles of H plus, okay? And so we put our initial amount of ammonia, that'll be 0.04 moles for all of these, each of these four parts. And then our change we put in terms, again, of that amount of H plus added when we add 40 milliliters, okay? And the whole idea of kind of titrations is as this free H plus is being added to the solution, we are going to shift to the side that makes hydroxide, right? In this case, we have hydroxide in our equation. We want to shift to that side because what is going to happen is the 0.02 moles of H plus being added will combine with the extra, or change 0.02 moles of hydroxide, right, in the change portion of the table. Those will combine and basically make water, right? So they're going to neutralize each other. So that's how you know that we're going to add 0.02 moles to the product side, subtract it from the reactant side. Okay, it all just has to do with that idea of neutralization. Now at equilibrium, we find that we have 0.02 moles of NH3 and 0.02 moles of NH4 plus. Okay, our next step is to solve for Ka, right? We're going to solve for Ka whether we start with a weak base or weak acid, because Henderson-Hasselbalch will always have pKa in it. And so our Ka for this would be equal to our Kw, which is a constant, 1 times 10 to the negative 14th, and we divide it by our Kb, which was given as 1.8 times 10 to the negative 5th. This gets us that our Ka is 5.56 times 10 to the negative 10th. We can find the pKa by taking the negative log of that, giving us 9.26. Okay, so below that I just write the Henderson-Hasselbalch equation. So the pH is equal to the pKa plus log of our ammonia over our ammonium. We plug in those values, and you'll actually see that it's a log of 0.02 over 0.02, which would be log of 1, and log of 1 actually equals 0. And so in this case, our pH equals 9.26, which is also just our pKa. And this is, again, the steps for before equivalence point definitely apply to this, but this is kind of a special case. We call it half equivalence point. And just the thing that's special about half equivalence point is basically, in this case, we're adding half the amount of moles, like half the number of moles of acid that we have of base, right? So we have 0.04 moles of base, and so we add half that amount of acid. So we add 0.02 moles of acid. And basically what results of this is our pH will just always be equal to our pKa, because the amount of our, in this case, base and conjugate acid should always be the same at equivalence when we're at, at equilibrium when we're at half equivalence point, right? They're both 0.02 moles, and so we should always get log of 1, which is equal to 0. So that's just a special circumstance, but again, the steps that apply to before equivalence point also apply to it. Okay, and we'll see the same thing when we add 60 milliliters, because we're still at, or defined as before our equivalence point. And so what we do is we start by writing our initial amount of ammonia, which again will not change from part of this problem to the next part of the problem. But our change this time, because we have 60 milliliters of acid added, we're actually adding 0.03 moles of H plus or acid. And so again, we'll add that to the product side because we want equal amounts of hydroxide to cancel out that H plus being added. And that gets us equilibrium amounts of 0.01 moles of ammonia and 0.03 moles of ammonium. Now our pKa shouldn't change from one part of the problem to the next, because it's still between ammonia and ammonium. The Ka isn't changing, and so the pKa won't change. So our pH is equal to our pKa, which again is 9.26, plus the log of the amount of ammonia we have, 0.01 moles, divided by 0.03 moles of ammonium. And we find that our pH is equal to 8.78. Okay? So that's, again, how you do the before equivalence. If you relate the work in both of these back to these steps, this gives you a pretty good outline of the direction you should take to solve it pretty much every time. They don't throw too many curveballs at you during titrations, typically. Okay, so the next step is when we're at equivalence point, which happened when we added 80 milliliters of strong acid to the base, right? And so this one is definitely the most complicated of the three categories. And so our first step would be to write the ice table, right? And again, just like last time, we're going to put change in terms of the amount of acid added. Again, acid because we're using the second option when we start with a weak base. Okay. Then we're going to find the equilibrium amounts of acid, which it should be all acid, right? When we find the equilibrium amounts, we should have all of the moles converted to NH4 plus, and the conjugate or the base should have none, right? We should have 0 ammonia left. You'll see that when we get to the ice table. Then you'll write a reverse ice table. So we're going to write it in terms of our conjugate acid or ammonium for our reverse ice table, which again you'll see. Then we'll solve for equilibrium amounts in terms of X, right? So we'll go through that ice table, solve in terms of X, remembering to convert moles to concentration. That's probably the biggest step that people forget to do, so definitely remember to do that. Then we're going to compare our equilibrium amounts to our Ka in this case, right? In this case, we'll compare it to Ka. If we started with a weak acid, we'd compare it to Kb. You'll kind of see why. And then we'll find our pH, and you can do so through our POH, or this time we'll be able to solve directly for it. Okay, and so here's the math behind it, right? So we start with 0.04 moles of ammonia, which we know, but we add 80 milliliters of HCl, 0.5 molar HCl. We actually find that we have 0.04 moles of H plus added. Okay, so just like before, we want equal amounts of hydroxide to neutralize that, so we have to add 0.04 moles to the product side. And what we find is that at equilibrium, we have 0.04 moles, or all of our moles, of our acid, ammonium, and no moles of our weak base, NH3. Now, because we were able to get equal amounts of hydroxide to completely neutralize the acid being added, meaning 0.04 moles, this system here will now just kind of be resting. There's nothing pulling it in either direction, and it will try to reestablish equilibrium. Okay, so that's why we see a reverse ice table. So you see the reverse ice table in terms of the conjugate from the first. So in terms of our conjugate acid in that first ice table. So we're going to write ammonia plus water goes to, ammonium plus water goes to ammonia and hydronium, or H3O plus, which again is just the same thing as H plus. So we're going to write our change in terms of X here, because we don't really know how much it will change. And then we'll write our equilibrium amounts. So it'd be 0.04 moles minus X for ammonium, and then X for both of our products. Now here, we want to relate it to our Ka, but remember our Ka and Kb have to be, or use things in terms of concentrations, okay? And our amount of ammonium, NH4 plus, is in terms of moles right now. So what we have to do is take that 0.04 moles and divide it by our total volume to find our concentration. And so it'd be 0.04 moles divided by 0.28 liters, right? It would be the 200 milliliters of base plus 80 milliliters of acid for a total of 0.28 liters. And that gets us a concentration of 0.143 molar, which I kind of write my equilibrium amounts of those again after. So my equilibrium amount of NH4 plus would be 0.143 molar minus X, and again our products would still just be X. Now I relate this to our Ka, right? So our Ka we solved for in the first part of the problem and found that it was 5.56 times 10 to the negative 10th, right? We needed that number to solve for our pKa, so we already had it. And you'll notice I ignored X in the denominator, right? I made that assumption. If you go back and check, it's a valid assumption. And we solve for X and find that X, which is also equal to our concentration of hydronium, is 8.92 times 10 to the negative 6. So we take the negative log of this to find our pH, which comes out to 5.05. Okay? So again, pretty much anytime you're at the equivalence point, these set of steps will be valid to use. So your first step should definitely be to identify whether a portion is before the equivalence point, at, or after, and then kind of apply these steps in this thought process to that portion of the problem. Okay, so our last part, when we added 100 milliliters of strong acid, represents when we passed the equivalence point. Okay, and so we're going to have more moles of acid than we did that ammonia base. Okay, so here we're going to write an ice table. We're going to make as much, in this case, hydroxide as possible. okay? And that's because we wanted to neutralize this H plus being added. Then we're going to solve for excess H plus, then convert that excess H plus to moles of excess H plus, which we can also convert to then molarity. Because it already would be in terms of moles. So you convert moles of excess to molarity, and then in this case we can directly solve for our pH. Okay, so again, 100 milliliters added, and so we actually added 0.05 moles of H plus. But you can only make as much product as your reactant allows, okay? And so we only have 0.04 moles of ammonia, and so we can only make 0.04 moles of both of our products. Okay, and so from this, we see that we go all the way to the product side, and we make 0.04 moles of hydroxide. Okay, now this will combine as much as possible and neutralize as much H plus as possible, right? So if there's 0.04 moles of hydroxide and 0.05 moles of H plus, that means we'd theoretically be able to make 0.04 moles of water, which we don't really care about. What we care about is we would still have 0.01 moles of excess H plus, right? Excess protons. Now the reason why we don't see reverse ice table when we pass the equivalence point is because the excess H plus is still driving that top reaction to the product side, right? If you had any more reactant, it would instantly become product, so it could neutralize any of the excess H plus. But in this case, we don't have any extra, and so we still just have a remainder of 0.01 moles of excess H plus. Our next step would be convert that to molarity by dividing it by the total volume. So total volume in this portion of the problem is 100 milliliters or 0.1 liter of strong acid and 200 milliliters or 0.2 liters of weak base for a total volume of 0.3 liters. That gets us a hydrogen concentration of 0.033 molar. We just take the negative log of that to find our pH, which is slightly below 1.5, and it's 1.48. Now again, the steps outlined in the slide prior to this work will work anytime that you are past the equivalence point. Just remember again, if you're starting with a weak acid, it would be these first words in parentheses that is applicable to your process. When you start with a weak base, it's the second word in the parentheses. Hopefully that clarifies anything. If people were still confused on that, if you have any questions, again, we'll be doing exam review and then also practice exam review 7 p.m. tomorrow night during that session. And then the video for that will be posted later on. Okay, so ask any questions you have then, and good luck studying.